All right, let's check out our next kind of chi-squared test. So the first main thing that we need to understand and know is that our chi-squared goodness of fit. So the chi-squared goodness of fit. Um, here is what the situation was with that one. We had one sample. Okay, so we're going to need to be paying attention to how many samples we had. We had one sample, and we were testing that one sample with one variable. Okay, now, for example, we have several categories in that variable. So for our M&Ms, that variable was color. So we had one variable distribution and one sample. So it was just very linear. We're going to see if this one sample is the distribution of that. Okay. But now we're going to have a little bit more multi-variable situation happening. So this is our chi-squared test. And on your calculator, you may have noticed that when we go stat over to test, that this is the one that is chi-squared test as opposed to chi-squared GOF test. Okay, so let's take a look at what that is and what that means. There's two kinds. One is called homogeneity, and that's the one we're going to talk about today. So chi-squared test of homogeneity. All right, and then chi-squared test of independence, which we'll talk about tomorrow. So let's think about that word homogeneous. We know that homogeneous means the same, okay? So we are going to then be doing this. We are going to test to see if two or more populations, okay, that's the key. So we're having two or more samples. That's the way I tell the difference. We have two or more samples, and then we are going to check those two or more samples with that one variable. I think I've seen it where there's could be more variables, but in particular, that one particular variable. So, and I have that stated here. If more than one sample from different populations, or if one sample from different populations are taken, then you are testing whether or not the solutions have the same rate of distribution, hence homogeneity. Okay, so let's take a look. I have three examples here, and we'll talk about what makes them homogeneity, chi-squared test of homogeneity. So here we go. We have a situation where here are the populations: senior adults, middle-aged adults, and young adults. So look here, three separate samples of 100. So I'm going to randomly select 100 from the seniors, 100 from the middle-aged, and 100 from the young adults. Three separate populations, three separate samples. Okay, then I'm going to check one variable, milk consumption. And in this case, yes or no, do they drink milk regularly? All right, so that's my one variable tested amongst those three populations. Okay, next. Here we have three populations: regular M&Ms, peanut M&Ms, and peanut butter M&Ms. So I'm going to get 500 randomly selected peanut or regular M&Ms, 500 peanut M&Ms, and 500 peanut butter, and then I'm going to check one variable for those, the color distribution. So I'm going to check and see if the variable color is the same rate amongst these three separate populations. All right, here's another one. Okay, so I wanted to show you this one because this is in an experiment. This one threw me for a loop. I didn't think of this as being three separate populations. And yet, this is how the chi-squared test of homogeneity showed up as an AP question. in 2016. Okay, so let's discuss this. So what happened was it was one sample of 150 women. So then I was thinking, oh, one sample, okay, but they were randomly assigned to 3 treatments. So they took that random selection of people, but then they randomly assigned them. So they're making essentially 3 different treatment groups, 3 different populations. The population of women who drink cranberry juice, the population of women who drink this lactobacillus drink, and the population of the women who, drink whatever mixture of whatever kinds of drinks that they typically have. All right. So the idea is that even though there's one sample, they are making up 3 different populations, the 3 different populations of the types of drinks. Okay. All right. And then they were just checking one variable amongst those 3 different populations. What rate did they get a urinary tract infection? Okay. All right. Moving on. So here are the assumptions that we are doing. So, wait, did I state what I didn't state what the null hypothesis and alternative hypothesis are. I'm going to find that for you real quick because that seems strange that I didn't write that there. So on the next page, the null hypothesis is that there is no difference in the distributions between the 3 populations. They're the same, or however many populations, okay? And then, of course, HA is there is a difference in the rates among those 3 populations. Okay, so then if we were talking our conditions, random, we stated and assumed that those samples are randomly selected from their populations, or they were randomly assigned to those treatments. We saw that on the previous page. So we had that random selection from the population for every sample, random selection of senior adults, random selection of young adults, random selection of young middle-aged adults, okay? And I remember that I had talked about this a couple of videos ago that 10% condition is actually not needed for random assignment, because does it make sense to say the 60 women randomly assigned to the cranberry juice drink is less than 10% of what? All the women who could drink cranberry juice or something? Anyway, so that doesn't kind of register. But we do know that the subjects that are in those samples, those populations, are independent of each other. So the senior adults are independent of the middle-aged adults, are independent of the young adults. Okay. So what is naturally making sense to you? I think it kind of starts playing out what it makes sense to state. All right. Large enough is, again, that expected counts are all greater than or equal to 5, but the expected rate is a little bit more complex because of this multi-variables and multi-populations. So let's come back to this. We'll revisit this expected counts here shortly. Let's look at how this works out and how we're going to organize our data and how we're going to do this in our calculator. So grab that calculator and then here we go. So first and foremost, what happens is, as you've noticed on this previous page, do you see our data is organized in a table of values with the 2 different headings, not just observed and expected. All of these in this table are observed. Okay, so multi-dimensions of observed, not just that single dimension of observed in list 1 like we had in chi-squared. Okay, so what happens then is we have to go and put our data in a matrix. And so we're going to kind of do a problem as we walk through this. So let's take a look at this problem on the next page and do our calculator, show you how to work everything as we do this. So here we go. So it is common folk wisdom that drinking cranberry juice can prevent or help prevent urinary tract infections in women. A 2018 British medical journal reported the results of a Finnish study where 3 groups of women were monitored for these infections over a 6-month period. One group of 50 women drank cranberry juice daily. Another group of 60 women drank lactobacillus drink. Do you know that that's kind of like, you know, doing a little Activia drink or a Yakult or something that's kind of like the yogurt-based type drinks. So those kinds of ones that have that, um, that type of bacteria, I guess, in there. Okay. And then the third group of women, 40 women, drank neither of those beverages. So we don't care what you drink, just stay away from these 2 things here. Okay, and they served as a control group. All right, in the control group, now we have the observed results of how many got the urinary tract infections. 15 in the control group had at least 1 infection, 26 in the lactobacillus, and 8 in the cranberry juice. All right. Does this study provide supporting evidence that these 3 groups experience urinary tract infections at the same rate? That's a weird question. That's like saying, does this provide evidence the null is true? I don't like that question. Okay, that's not statistically sound question, so I don't know why that was there. Okay. Additionally, does this study provide supporting evidence for the value of cranberry juice in warding off urinary tract infections? All right. So remember, we're not going to list out our parameter, but here we'll go to our hypothesis statement. So we would say that null hypothesis, the women get the UTI infection at the same rate, regardless of the type of drink that they consume, the treatment group for drink they are in. Okay. The alternative, they do not get urinary tract infections at the same rate if they consume these different types of drinks. So, conditions. So it's assumed that these Finnish women are randomly assigned to the 3 treatment groups. Okay, so that was then on the independent, again, I'm then assuming that these Finnish women only consumed that type of treatment. So in other words, the women in each of these treatment groups are independent of the other women in the other treatment groups. So nobody was in more than one group. Okay. Now, let's talk about this. The large enough. All expected counts are greater than or equal to 5. And I'm going to show you how to do this momentarily. So we would then conclude with the chi-squared model applies. So let's take a look at how we're going to organize our data. So we need to go ahead and organize our information in an observed matrix and an expected. A lot of times they'll give you this observed matrix already written out. They did not, so I had to write it out from the paragraph information. So what they had told me was 50 were in the cranberry group, 15 of them got a UTI, 60 were in the lactobacillus group, 26 got a UTI, and 40 were in the control group, of which 8 got a UTI. And so then because of subtraction, of course, I filled in the others. All right. So let's talk about this expected. This expected is happening because I need to see like what overall rate was the UTI happening or in the cranberry juice happening and overall rate of the UTI. So what ends up happening to do that is we end up taking the total of our, so I don't even know what that total is. What is that? 15 plus 26 plus 8. So that's 41. Is this 49? I don't know because I'm bad at adding and subtracting. And then, so then whatever that would leave us with there. So 99, 101. Is that okay? Which, yay, that's 150. Okay. So here's what happens. So say I want to determine, okay, what's expected here? Okay. Well, then here's how we do that. I can see cranberry juice is 1/3 of the total in the sample, or the total in the experiment, okay? And then of those, then here is the UTI rate, 49 out of the 150, okay? And so what happens is, to get what was expected right here, is we want to do, okay, this rate, okay, in terms of this amount of UTIs. So on that previous page, I had talked about the way to get that expected counts for each cell by taking that row total, multiplying it times that column total over that total. Because see, in this case, if you think about it, here was our this right here was the rate at which the cranberry juice people were in the sample. And then we did it in terms of how many UTIs there were. Okay? All right, so that means to come up with this value right here, we would do row total times column total over the total, which is 150. So if I did that right there, that's 1/3 of 49, that's 16.333. So for every one of these boxes, you can compute them by hand. And in some cases, some data is presented to you to where you actually have to do it by hand. There's no calculator option. Now I'm going to show you how if you have all the needed information, then you can get all of these expected values already computed for you. And so I'll show you that. But regardless, you need to know how to find each one of these cells without all the total data. Because I've seen problems and I've seen information, so this is obviously something that you're expected to understand, where maybe you only had the total of this, the total of this, and the total. These other bits of information were not given to you, and you were asked to come up with the expected value right here. So you would go row total times column total over total. All right. So let's move on. Here we go. So we need to learn how to put our data into our calculator, into the matrix, because it's multidimensional. So we're going to go to this location. We're going to get our calculator, and we're going to go second matrix, which is second and then this x to the -1 right there. Okay? Now, I show that to you right here on this page. Here it is. Second x to the -1. Okay? Second x to the -1. Now, tab over to edit right here. And you're going to enter your observed data into matrix A. Now, you can see I already have data in there. Look, I've already had a 3x3 matrix. So watch this. When I tab over, I don't know how to clear these things out actually. So if I go enter into this, there's already data. Well, it's okay because you can type over the data. And so I've not really ever worried about clearing those out. But we do need to make it the correct size. If this one that we're going to do is a 2 rows and 3 columns. So I'm going to do 2x3 instead of what I used to have in there, which was 3x3. So I'm going to do a 2x3 matrix. See, then now it's the correct size. A lot of times I can never remember which comes first. Is it 3x2 or is it 2x3? And so a lot of times I have to just kind of like put those numbers in there until I figure out, okay, that's not right. I guess I need to do it 2x3. Okay, so that's how I kind of just play around with it until its shape is the correct shape of my data. And so let me go ahead now and put into it the information that was observed. We had the 15, and then I hit enter, and there were 26 in the lactobacillus, 8 in the control group. That made 35 not getting a UTI, 34, and 32. So there is the observed data for our experiment with the cranberry juice, the lactobacillus, and the control. There is the observed. Now, here's what you do next. So next, after we put that in, then we are now going to go and run the chi-squared test. Make sure you do not run the goodness of fit test, but the chi-squared. So here we go. Stat, tab over to tests. And remember, you get there quicker if you actually go up. So here it is, chi-squared test. So I'm going to hit enter. All right, and then it asks you, where is your information? So my observed information is in matrix A. Well, the cool thing about this is if you have all of that information, then, since it's a formula, row total times column total over total, then the calculator can do that work for you. It can compute the expected matrix for you. So this is essentially asking you, where would you like for me to paste your expected values? And you say, oh, I want you to paste them into matrix B, okay, because that's the default. So let's go on down there and calculate this. Here we go. And look at there. There's my chi-squared value. There's my p-value. And we're going to discuss this degrees of freedom. What in the world is that? How is that 2 when I've got all these multi-dimensions? Weird. So let's take a look. So the expected has been computed and put into matrix B. And let's go ahead, I guess, and talk about this degrees of freedom right now. Since it is multidimensional, it's not just categories minus 1. So here we have another thing that's different. So it is not categories minus 1 like the goodness of fit test. Okay? It is your rows minus 1 times your columns minus 1. So what was that for our test? Let's see. We had 2 rows. So 2 minus 1 for the rows and 3 minus 1 for the columns. And if you multiply that together, you get 2. 1 times 2 is 2. So that's the degrees of freedom. All right, so coming on over here, we see that we need to still put in this expected because I got to show you why I knew that all expected counts are greater than or equal to 5. So let's do that. So these, remember I told you that the calculator pastes the expected values into matrix B. So let's go and look at that. I want to view matrix B. So let's go back to our little second x to the negative 1. Now, you could scroll down and hit enter and look at this matrix B. FYI, look, it changed the size of matrix B when I ran that test. Okay. But I'm going to tell you, I'll go ahead and show it to you. Enter. Okay. This has got a lot of decimals and stuff. It will actually be easier and better to see if you look at it in edit mode. So watch this. If I go over to edit and then go to matrix B, see, that's a bit nicer. So I prefer to look at my matrix B in the edit menu. Okay, it comes out nicer. So that is the picture that I copied and pasted right here. So therefore I know all of the expected values, the expected counts are greater than or equal to 5. So that is, so look, you show this. Hey, look, these little guys are large enough because as shown in the expected matrix below, and that has to be there. You can't go, wink, wink, just take my word for it. No, it's always about proving yourself. So you prove yourself there, and that's what you got. Okay. So our test statistic was our chi-squared of 6.18, 0.45, degrees of freedom 2. So our p-value is less than alpha. And we're going to make a decision to reject the null just barely, but we rejected it. So since the p-value, oh, why did I do that? Is less than, the p-value is less than alpha, I reject HO. Okay, so that was weird. Less than alpha, I reject HO. And so there is evidence that HA, urinary tract infection rate among Finnish women, is different for those who drink cranberry juice, lactobacillus, or the control group. Okay. All right, so there's the basics of that test. So what I would like to do is stop right here. There's actually one additional main thing we have to talk about. And it is this thing called standardized residuals. But there's a lot involved here already. So I'm going to actually talk about this standardized residuals in the next video and then go over, oh, is that all that's left? Okay, well then never mind. I'll go ahead and finish this out. Let's do this one last thing. Here we go. If you reject, which we did, if I find there is a difference among the rates, then we need to kind of give more information. Well, where is the difference? How much is the difference? What's going on with that? So we're going to do that with what is called standardized residuals so that you can better understand which components contributed mostly to this chi-squared value. The standardized residuals are not on the formula chart, so that's annoying. It's basically kind of like the square root of a chi-squared. You know, it's observed minus expected, so without the squared, over the square root of expected. So we essentially, if you remember, our chi-squared formula that's on the formula chart is summing up the observed minus expected quantity squared over expected. Well, if you take this right here and you just think of it as square rooting it, it's not, then that's what we have. The observed minus expected over the square root of expected. That's going to give us a standardized understanding of how far away the observed was away from what was supposed to happen in every single cell in each cell. Furthermore, the good thing about this is, see, look, remember we squared to kind of take away those negatives? Well, this shows the direction, the negatives or the positives, because it's not got that squared taking that away. So that's important because if I have a negative residual, then I know observed was below expected. If I have a positive residual, then I know what we got was more than expected. Okay, so let's take a look at this. So once you then have created this standardized residuals, you can then interpret them, whether they are above or below the expected value. And you can kind of get a sense for which values were farther away from expected than the others. Okay, so let's do this for our lactobacillus data. Here we go. Standardized residuals. So look at what I did for this one cell. I took, okay, so I think I have it on the previous page, okay? So for the cranberry one, I did this, okay? Observed minus expected divided by the square root of expected. So I did that 15 minus 16.33 over the square root of 16.33, and that's the standardized residual. How far away from expected? So this is telling me those women who had cranberry juice at treatment got urinary tract infection at a lower rate than they were expected to. Okay? Now, contrary to that, look at the lactobacillus one. So let's study that. Here we go. So I'm going to do this. I'll do this in a different color. I've got this here. Observed 26 minus expected 19.6 divided by the square root of expected. Okay, so I come over here and that gave me a positive 1.45. So the women in the lactobacillus treatment got urinary tract infections at a higher rate than expected. Okay? Now, this is interesting. The control group ended up being this negative 1.4. So that's interesting. Look, that kind of tells me, do I think cranberry juice is doing a really good job? I don't know. There's probably some sampling. I don't know what's going. I don't know if cranberry juice is necessarily working, but I think I have an indication that this lactobacillus is making us have the urinary tract infections. The cranberry juice isn't necessarily even working, reducing it as much as the control group. So that's interesting. All right. So once we do all of that, we typically want to talk about our specific conclusion, and we're more looking at the one that is most outstanding and meaningful. Okay? So here we say, I can see from the standardized residuals that women in the lactobacillus group are getting UTIs at a higher rate than expected. It's all about higher rate than expected or lower rate than expected, with a residual of positive 1.45. The women in the cranberry juice treatment group getting UTIs at a lower rate than expected with a residual of negative, but the control group actually got UTIs at a lower rate compared to cranberry juice. So that was interesting, as evidenced by that standardized residual of negative 1.4. Okay, so in summary, the standardized residuals is giving you more detailed information about the specific components within that matrix, okay? Because we had multivariables at play, the type of treatment, and then the variable of getting the urinary tract infection or not. Okay, so chi-squared test of homogeneity, multiple populations. So multiple samples from the populations that we are testing with one variable. Okay, then we talked about the whole different way of putting these into your calculator. You have all of this right here. How to get these new degrees of freedom indicator. And then how to finally do a test and conclude specifics from the standardized residual. Okay, so there we go. Chi-squared test for homogeneity. And so then you will complete, I think, one free response, which is that 2016 AP free response question, and then some multiple choice questions related to this. All right, so good luck to you on that.